Hello, everybody. This is Tim Lankish here. We're gonna wait a couple minutes for everybody that's logging in now to jump online. So sit tight, and we'll get started here in a couple of minutes. Okay, looks like quite a few people have logged in, so I think it's time to get started. So again, welcome everybody to CAE Services Ask the Moleflow Experts webinar. This is a monthly thing that we've been doing on various topics about Moleflow analysis, and the topic this month is two-shot overmolding. This is a little bit about me. Those of you who have attended these webinars have seen this before, but I've been around Moleflow circles for quite a while, and that's my background. I've trained a lot of people, done a lot of analysis myself. This is a little bit about CAE services. We've been around since '88, and we've got the most expert certified Moleflow engineers in the world. We are an Autodesk partner as of last year, and we've completed some 24,000 plus Moleflow projects, and quite a few of those are two-shot projects. So let's just dig right in here. What is overmolding? Some definitions are in order. Overmolding is molding one material over another. Pretty straightforward. You could have insert overmolding. That's plastic over an existing part. Some insert, whether it's metal or another plastic piece, or any other material for that matter. We're going to skip over insert molding for this webinar, only because I've got quite a bit of material to cover for the two-shot sequential overmolding, which is, as it implies, two shots in sequence. You mold one part or mold one shot, and then rotate the mold into the other shot. Then you could have multi-shot molding where you have more than two shots in sequence. So some of the benefits of overmolding: functional, of course. You're adding characteristics to the part that are unavailable from the base resin. For example, TPE grips are very common, like in a toothbrush. You know, it used to be toothbrushes were just all plastic with the bristles in there, but you know, more recently they've added the TPE grips, or you see that screwdriver there. That's insert overmolding and two-shot overmolding in the same thing there. So the metal piece of the screwdriver is the insert. We mold one type of plastic over that, and then another type, the grip for it over that. So they're very functional reasons to use two-shot overmolding. You could have watertight seals for cowls and windows, for example. And then there's practical reasons to use overmolding. You can avoid secondary operations such as assembling two different plastic parts together, or inserts and plastic parts, and economic reasons to avoid the cost of having additional molds. You can obviously run them in one mold. So those are some of the benefits. I'm sure there are many others, but those are probably the most common. So how does it work? Here's just a basic look at how things work. So we have a first shot that we're going to mold here in this station and rotate it over to this position. And then we're also going to mold another shot in the first position while we are molding the second shot over top of it in the second position. We eject the second shot, rotate the core, and go at it again. So that's the basic process that's used for overmolding. Here's a typical two-shot setup. We've got a manifold for the first shot over here, and we have a manifold for the second shot over here, molding over top of the first shot. So some of the typical problems that we encounter when we're talking about two-shot, there's a lot more limitations on gate placement than you would have with a typical single-shot injection mold. Some of that's due to tooling. You have to accommodate the rotating core, and maybe there's slides and lifters and things that need to be accounted for. A lot of it's due to aesthetics. You want to maybe hide the gate from the first shot when you're thinking about the second shot. So you may automatically, in the first shot, want to put the gate in certain locations so that when the second shot molds over it, it hides it. Oftentimes we'll have multiple regions in a second shot. This is very common with sealing applications for like a cowl of some sort, where you have multiple TPE areas that are molded over top of the larger substrate, and those regions tend to be very different sizes, for which we have to balance the flow in the second shot. Another common problem we have is gas traps against the first shot that can't be vented, and I'll show you an example of that. And then of course we have warpage. It's same types of warpage issues you get with a single shot oftentimes, but in this case now we're dealing with dissimilar shrinkages oftentimes between the two shots. So you have to account for that when you're thinking about warpage. And then sometimes the cooling of the two shots together can be difficult to simulate. So of course cooling matters, and we have to find some way to account for that when we're thinking about warpage, because obviously cooling is a big contributor to warpage. Now we also have bonding of materials can be an issue. So let's talk about the different ways we simulate things in mold flow. We often will model it as two separate shots, and that gives us a lot of advantages when we're playing what if up front. We can use it to determine gate locations, determine each shot's process, and we have different meshing options available for that. We can use a midplane. To those who are familiar with the different types of mesh in mold flow, we could use midplane mesh, we can use dual domain mesh, or we can use 3D. So that's one way to do it, is separate shots. We can model the two shots together. And again, midplane and dual domain, if we use those, we can only do that with fill and pack, and that's not typically what we're going to use those for. So we typically rely on a 3D model when we're going to model the two shots together. We can do it with just fill pack warp. That's the traditional way. And if you want to look at the cooling of the second shot, you can use the first shot as what we call a part insert. or you can actually run a full 3D with transient cooling. So this is newer to the mold flow world, and that's only for 3D. So where actually the two shots, the heat transfer from the first shot carries over to the second, and vice versa. Let's go through some examples here. So this is a case when we're looking to find the gate locations and the process that works for each shot individually first. Oftentimes, as I said before, you're limited by your gate locations because of aesthetics, and that this is certainly a case here. So in the first shot, we were kind of limited to this area as an area that we could place the gate, because this area over here was going to be visible. And then similarly for this location over here, we wanted to keep this off into the same area. So we had to deal with the consequences essentially of having limited gate locations. You can see the filling animations that result from those. So things that we're going to monitor when we're limited with gate locations are of course pressures, the processability. We have to make sure that the pressure and the clamp force and all those things that we would do for a single shot analysis fall in line with the capabilities of the machine and so forth. And then we look at the second shot here, and we immediately notice something unique to two-shot analysis. And we have this air trap here, and that air trap is pushing up against the first shot. The air trap on the second shot is pushing up against the adjacent material on the first shot. And that's a bad deal. As we know with air traps, if we don't have a way to vent those, then bad things happen. And those bad things typically either result in a short shot, or you compress the material in that area. You can superheat that material and cause burns, not only in the second shot, but also in the first shot. So we have to be careful about how the filling pattern plays out with regard to venting. And we want to try to get this out to the ventable parting line if we can. And in this case, this was a part design issue. We have it's two things, this part design issue, but also the limited gate location. But this thin area here is causing some hesitation in the flow front going around that window area. So how do we fix two-shot flow problems when it's something like trapping air? We can modify the part design with flow leaders or flow restrictors. We can try to move gates, but as I've said, the gate locations are often limited due to tooling issues or gate vestige appearance issues. So sometimes what we'll do is we'll actually simultaneously be building a midplane model. And of course, we're going to verify the air trap, and it shows up in the exact same spot. One quick warning about using midplane is oftentimes in two-shot world, some of the wall stock cross sections tend to be thick and chunky. So midplane in some of those cases doesn't do as good a job of predicting filling patterns. So we have to pick our spots here, but where we can, we want to use our midplane models to help us get to a final answer a lot quicker than we would have with like a 3D or a dual domain analysis. So we verify the problem that we saw in the 3D simulation, check that box, and then we start playing around with wall thickness, which is a very quick thing to do in midplane. And in this case, we put a band of material around the rim here that was thicker to promote flow around that window and close up that flow before it causes an air trap at that perimeter. Not only that, but we wanted to install a flow leader from the gate area out to that thicker band. Again, it's pretty choppy in the midplane world here. We can just pick some elements and make some thickness changes. Of course, it's going to be much smoother in the final CAD model, but this is the nice part of playing what if when you're in midplane. So we have a blended flow leader with a thicker section that was needed to help promote that flow out to that rim, and then the rim kind of takes over from there. So we do the flow analysis and we do a final check in 3D, and you see, of course, where the knit line used to be out here and the air trap now has been pushed out to a ventable location. And as you can see with the actual molded sample there, that we were able to confirm that air trap location. So problem averted on that, and that's one way to solve that type of problem. The other problem we're often going to come across in two-shot is knit lines. This is a shot looking at the two-shot, a second shot, I should say. And in the initial gating that we were handed on this, you can see how this filling pattern plays out. Nice, pretty balanced gate locations, maybe a little bit off balance left to right, but not too bad. But you see all these knit lines forming in these areas, which are actually visible knit line areas. And so after playing around with some gating scenarios, this is what we came up with. And sometimes we have to install these tabs at the parting line to be able to gate, so that we don't have a gate vestige in a visible area. But you can see we were able to get a lot of these knit lines off of the visible areas. We wanted to keep them concentrated in these areas here. And we've got a nice flow balance here between the top and the bottom. So this is the result of, oftentimes 20, 30, even 50 iterations sometimes when we have very difficult geometry to deal with. But, it's a very useful exercise. And you can see here how the knit lines played out. So that's an example of keeping the shots separate and how we play with gate locations and process and part design to get the filling patterns that we want. The next step would be modeling the two shots together. Here's another example in the lighting world. So as I mentioned before, it's 3D. We can run fill, pack, and warp, or we can use the first shot as a part insert when we want to add cooling in there. And that's been the traditional way to do it in Moldflow over the years. And when you do that, you have to set the insert to the mold temperature so that the additional heat transfer between the first shot and the second shot is somewhat accounted for. So here's a filling pattern for the first shot. And this is one of those cases right here where you can see in the second shot, this area is going to be molded over this. It's almost like a sandbar there in the middle. So this is one of those cases where the gate location for the first shot, it was necessary to put it in an area that was going to be covered up by the second shot. Not the best for processing. There's still some imbalance here, and with this type of material, oftentimes the pressures kind of go through the roof. So, ideally we'd have a better gate location for balance, which would probably be down in this gutter down here. But we can't do that because that's a visible area. So we can't have a gate vestige there. We have to put it on there. And then we go to the second shot and we see what we're trying to do is keep knit lines in areas that are not visible. And it's hard to tell from this part what those areas are, but the knit lines and the gate locations are set up to get those knit lines in areas that are less visible. So when we go to warpage analysis, this is what things look like when we do it two different ways. The first way on the left here is to model the first shot as a part insert. And the second way is to keep the two shots together so that the stiffness of those two shots and the residual stresses from the filling analysis of the first shot are carried over to the second shot. This is what the warpage looks like when those are put together. No cooling was included on either of these, but you see what happens here. We got almost a complete reversal of the warpage results. So I'm inclined to go with the two shots together, and there's still discussion among a lot of clients that we have out there as to which way is actually giving us more robust results. But ideally, you want to be able to put things together, have the residual stresses transfer over from the first shot to the second shot, as well as the heat transfer, and have it all in one big happy model here. So again, no cooling included here, but we have to be careful about how we interpret results when we're modeling different ways. There's even some indications that the types of materials that are used, whether it's amorphous or semi-crystalline materials, in some cases one type of modeling works a little bit better than the other. So we are working towards getting better results and having it be able to be all included in one model, and ideally that's where we're going to go with the two shots together. And then to take it a step further, the full 3D with transient cooling, this is kind of where it's all going to end up. And eventually this is going to be a lot more practical than it is currently, but we are capable of doing this, where we have the first shot over here, we have a second shot over here, and we can actually define the rotational half of the mold such that we get the heat transfer between the two shots. So, we mold the first shot, the heat that builds up from the cooling of the first shot rotates over and becomes the initial conditions for the second shot, and vice versa when it transfers back to the first shot. So that's really how it happens in a two-shot mold, and we can set our mesh up so that is the case. We give this properties of the rotating half, and then we model the two halves of the mold separately in a full 3D transient cooling analysis. So what it does is it'll track the heat over one full cycle. So you see this is an area on the first shot here, and how the heat or the temperature changes in that area, and then the second shot here. So it follows one part through one full cycle of molding the first shot and then molding the second shot. You can kind of see that play out here in an animation. On the left side we have the cavity view, on the right side we have the core view. So I'll just kind of let you watch that for a second, but you see things heat up on the one shot and then they cool down and then they heat up again on the other shot. It might even be better to view from a cross section here. If you follow the first shot, that gets hot, and after that one gets hot and cools down, you'll see the second shot over here heat up and cool down. So it kind of bounces back and forth like that. And I should note, admittedly, this isn't the greatest cooling design. It's really here for just to show exactly what it's doing there. So here are some of the warpage results. This is the length direction, and I've kind of compared all of the different methods for doing a warpage analysis with two-shot. So the upper left, we have the first shot modeled as a part insert with no cooling. First shot part insert with cooling, and you can see not a whole lot of difference between the two there. And then we have two-shot overmold with no cooling and two-shot overmold with cooling. So one of the big things that you're going to notice here is that the length direction has changed quite a bit. 0.4 from 0.3, so that was a 33% increase in the deflections there. So what that's telling me is that the shrinkage from the first shot isn't really being accounted for when you model it as a part insert, and that makes a lot of sense. Because when we do the two-shot overmolding, we're doing the full fill pack analysis, and of course the shrinkage from that is going to be considered when it marries up with the second shot. And then down here we have the two-shot overmold with the cooling on there. So you see some differences in the deflection of that far edge there. And my point in bringing all this up is that there are differences in the results depending on how you model it. Here I've exaggerated the results a bit by a factor of 10, and now we're looking at the width direction. You can see how things change when we model things as part inserts and when we model the two shots together using the overmold. So even when we add cooling to it, you can see that this outward bow kind of goes away. And any type of box structure, when you have cooling in there, add cooling into the analysis, typically it's going to make it bow inward a bit more. So we kind of see that playing out where the cooling is making a difference there. And then we have the vertical direction as well. So part design. So just to wrap that piece of it up, those are different ways to model things in mold flow, and the takeaway from the two-shot overmolding with cooling is that it's a difficult thing to do in mold flow at this point. It can be done, and we're at a point right now where we really want to move forward with this and get a lot more feedback and data to see what really is the best approach on that. Part design considerations. Rules of thumb still apply when we're talking about designing for two-shot versus just single shot. You want uniform wall thickness wherever possible. Your rib to wall ratios should still be in check. You don't want to introduce sink where it's not necessary. Flow length considerations become a little bit more dangerous here for the reasons I stated before. You're putting gates in locations where you typically or oftentimes would have longer flow lengths because you're limited on where you can and can't gate. Then you have material bonding issues. So two ways to bond. You can do a mechanical bond, as you see on the right, different ways to kind of poke holes through your part and let the second material flow through and kind of grab onto the first shot. Or you can rely on remelt to induce a bond between the two materials. Sometimes materials just chemically are not good at bonding together. So depending on what types of materials you're molding, you may or may not be able to rely on the remelt. So here's an example of, this is kind of a typical application that we see in two-shot. This is the old Chevy bow tie here. We have varying part thicknesses in a sandwich scenario. The inner shot's polycarbonate, the outer shot's PMMA. So how thin can we go? We have a 2.5 millimeter max total thickness available to us, but can we thin it out? Can we use less material? This is one of the questions that we can answer, and often it's a trade-off. Maybe we thicken one, thin the other, so forth. I've done many simulations like that. But for this one, we have 2.5 millimeters available to us, and we want to see how this plays out if we try to thin things out. So first thing we notice here on this shot, this is the outer shot. And again, we're separating the two shots into two separate analyses here. But we notice that we got some race tracking going on in these thick sections. We go back to here, you see this thick section right here, and that's causing some race tracking around the perimeter and potentially kind of a nasty little knit line here that might show up on the surface. Pressures are fine. We have no issues with the pressures. Of course, we're going to be adding a manifold to this, so we need to account for that at some point, but in the part itself, our pressures are good, they're balanced, no issues there. And then we look at the second shot, and we look at the original design at 1.5 millimeters, and we see 9,600 PSI. Again, need to add some for the manifold system, but just adding that shouldn't put us in any danger area. But when we go down to 1 millimeter, look what happens. Now we've got 16,390 PSI. You add a manifold to that, maybe a few grand. So now we're up to 19, 20,000. Then don't forget the injection molding machine nozzle and the pressure drop that is included in that. So now we're in the danger zone here. So this is good information to have about whether or not we can actually go to the 1 millimeter. So the final design that we ended up with, you see here's the original where we had the thick section here. We actually ended up thinning that one out because that was going to be the show surface and thickening this area here. And this isn't actually the final design. The actual final design had that rounded off a bit. But look what happened to the knit line on the outer. It wants to get there. It wants to try to create a knit line, but it evens itself out pretty well. And then we actually started inducing a little bit more of that flow race tracking on the second shot because we thickened that area up, but not to the point where it was going to cause any concern for a knit line. So that's the what if that you can do with part design when it comes to two shot, and you want to see which shot you need to thicken, which you need to thin, and what, so to speak, can you get away with it on that. So there's some part design considerations. Now the processing considerations. Valve gate sequencing is a very common thing to do, not only on first shots oftentimes, but more commonly on the second shot. I showed you an example before with placing knit lines where we want them. Valve gate sequencing is a great way to do that as well, especially for fine tuning on very complicated part designs. Running different fill speeds, you got to be paying attention to this. Sometimes that matters to make sure that the speeds that you're running are actually attainable by your molding machine. Melt temperature is something that you may need to be running a little bit higher for better material bonding sometimes, for example. And we can use the remelt zone plot in Moldflow to evaluate that. So here's an example. Here's a cowl where we have the substrate in blue there, and we have the overmold in the purple. So we have 4 separate areas. 2 of them are the same size, and these 2 others are the same size as well, but they're much smaller than the first 2. So here's how that looks in a manifold design for the second shot. So we actually did some bore balancing on this, created bores that were much smaller to the smaller pieces to hesitate the flow to them so that they result in balanced filling with the 2 larger pieces. Now, if you don't have a balanced manifold and you've got some of these parts filling a lot earlier than others, you might overpressurize them. You might see some leakage of material from the second shot onto the first, that kind of thing, or you may, blow some area open at the parting line. So that would be a reason to do that. You could also use valve gate sequencing to help control the flow between different shots here too. This is what a remelt zone plot looks like in Moldflow for 2 different examples that we've shown already. So in order for something to be considered remelted, the temperature of the first shot has to exceed the material's transition temperature, which is essentially the definition of melted material. When you have remelted material, you tend to get better structural bonding between the 2 parts. But one of the downsides to that is having unpredictable changes to the shape of the first part. So if you get excessive remelt, for example, you could actually, let's say you've got an optical piece that you're molding, and the first shot melts too much, and then that can change the optical properties of that material. So this plot will help determine which areas are seeing remelt and which areas are not. And obviously you want that to be spread as evenly as you possibly can across the first shot where the 2 pieces meet. We also have the ability to show sink marks just like we do on a single shot analysis. It used to be in 2 shot you couldn't show the overmold sink marks, but now we can. And then other Moldflow capabilities include compression overmolding, injection compression overmolding, and 2-shot windage analysis. That's something that we're dipping our toes into a bit here, and that's a real challenge. And the jury's still out on this a little bit in terms of how do we control how the 2 parts mate together when we're bending one versus the other. So 2-shot windage analysis is essentially the same process as as a single shot windage analysis, but the trick is in the morphing of the part in CAD and how, again, that mates together with the second shot. So this was Ask the Moldflow Experts. Some questions had come in, that were submitted by you guys, and I'll hit a few of those. Some of them are kind of repeat of what I've already talked about, but one of the first questions I got was, can it be simulated in Advisor? So for those of you who don't know, there are two Moldflow programs. One's called Insight, which is the more in-depth, fully capable manufacturing solution of Moldflow. Advisor is more what the name implies. It's an advisor analysis. I don't like to call it stripped down version of Moldflow, but we'll go with that for now. But can overmolding be simulated in Advisor? The answer is no, not explicitly, but we can do the same things in Advisor that I mentioned before when we separate the shots. We just can't see how the two shots interact with each other. Someone asked what the #1 challenge in transitioning from single shot to two shot is. I mean, you could pick any of the things that we talked about, whether it's air traps, paying attention to that. I would argue that maybe the single biggest challenge is knowing where to put the gates, because of the limitations that you typically run up against with running two shot. Material bonding, we had a lot of questions about material bonding. I covered that. Limitations and shortcomings of Moldflow, I would say that the biggest one there really is the being able to include cooling, which we certainly can do, but that technology is still maturing. It's getting better, and we have more tools at our disposal than we had before. So as Moldflow continues to mature in that world, it really boils down to the modeling of it, and then getting good feedback and good data to know whether or not that really is a shortcoming anymore. But we have a lot of workarounds that we can work with for now, and we'll continue to work on the two-shot overmolding with cooling, and then warpage, of course, with both shots together. Lots of different ways to handle that, and again, with the introduction of the two-shot overmold with cooling, that will get better and better. And yeah, one of the other questions was about shrink rate assumptions for the second shot, plastic versus a metal substrate. So there are no shrink rate assumptions if we model things as a part insert. It's assumed to be the size it is, and it won't shrink if we mold over it. But when we do put parts together, if we're doing a two-shot sequential overmold, or we're doing a molding over a metal substrate, those things are accounted for. So when it's plastic over plastic, we have the shrink rate of both materials involved to some degree. So the first shot gets molded, it stays in the mold, but it has some residual stresses in there as it's being molded over with the second shot. So, but all of those things are accounted for by the material data. So to the extent that you have good material data, yes, both shots and their shrinkages are accounted for in the way they should be accounted for. Same thing with molding over a metal substrate. Now we're talking insert over molding, and that metal is going to hold its ground. It's not going to move. So you have to be aware of that, and that is accounted for in Moldflow when we mold over metal. So those are some of the questions I got. If you have any other questions, feel free to email me at any time. I don't know if anybody put any questions out there on the GoToWebinar forum there, but feel free to email me anytime, and my email address will be coming up here shortly. But what's new at CAE? We talked about the Autodesk partnership. We're responsible for software sales, training, and mentoring. With software, we have demo days. If you have a part that you want us to look at and you're considering purchasing software, we'd be happy to look at that part with you and do a demo with your part on the Moldflow software. And if you've got a two-shot analysis, even if that's something you want to look at, we could certainly do that. On the learning side, we're building expert analysts. That's our motto. You see the hat there. So if you attend any of our training classes, you get one of these hats. We have both classroom and online training. Of course, with COVID, it's pretty much online, but we are opening the classroom now. So if you're looking to get trained in mold flow, you can certainly come here to our office in the Chicago area. This is the Ask the Mold Flow Experts monthly topics, and our next one is what's new with Mold Flow 2021. So yes, Mold Flow 2021 is coming out soon, and we're going to talk with some folks at Autodesk together on our next webinar about that. Some exciting things coming down the road on that. We have office hours. Pick a topic, sign up for some office hours, and just chat one-on-one with me or one of my guys here about anything related to mold flow. We have our new website. Of course, you can go there and you can follow us on LinkedIn. So for me, if you want to email me, it's just tim@caeservices.com right here. And we want to thank everybody for attending. We know there's a lot of webinars being done during the whole lockdown scenario here with COVID. So we appreciate you taking time out of your day to stop by and check out what we have to present here. Don't be a stranger. Feel free to call or email at any time with any questions. I'd be happy to answer them. So with that, I'll say goodbye and thanks everybody for attending.